Yeah, thank you for inviting me to this wonderful place. I'm a geophysicist by training, actually, and I turned planetary scientist after my postdoc at UCLA back in the 80s when my supervisor introduced me to planets. And I got interested in astrobiology, actually not knowing that we did astrobiology, but I used to do thermal evolution calculations. At one point in time, I thought, well, look, I mean, we have radioactive decay, we have convection in there and everything. But what about life? I mean, is there a feedback from life to planetary evolution? We know about the atmosphere, but how about the interior? And I think that was in 2008 something, or a little earlier, 6 maybe. And so we wrote a proposal to a German funding agency, and we got the funding, and that was very good. That started some of the work that DLR then picked up doing in what we then later learned is called astrobiology. At the time, we were only thinking we do planetary sciences. Anyway, so I was asked to put together some introduction into formation, evolution of planets. Now, you should be aware that not all of what I'm treating today is what I'm expert in. So, some of the stuff is, just like I understand it, and I'm trying to pass it on to you, my understanding. But I'll try to do that such that you get an introduction and can pick up, from there and look at the literature if you're deeper interested in these processes. Now, this is my outline. I would, spend a little bit of time speaking about habitability and concepts of habitability. Then I'm spending some time on the formation of planetary systems, what people are doing these days to better understand how the planetary system, or our solar system, formed, and how that would apply to planetary systems more in general. And personally, I believe that the use of the exoplanet studies that we have so far to date actually is more in a sense of better understanding how planetary systems form rather than how planets themselves are working, because we don't have enough data. Although it is interesting, and I will show you some of the results, if you increase the size, what happens to a rocky planet if you make it just bigger. Then I will spend most of the time in the evolution of terrestrial planets. So I'm not really going into giant planets, although these are of great interest to exoplanetary studies. But I concentrate on terrestrial planets because we're looking at it from the perspective of astrobiology. I will talk about surfaces a little bit, interior magnetic fields, how they're generated, atmospheres, and life. And I will conclude with a model that a student of mine and I are sort of promoting these days that would couple plate tectonics and life and continental growth and so forth together in an integrated system. I hope I can convince you that some of that stuff makes a little bit of sense. Now, just a motivation slide. I believe that finding life beyond the Earth is important, and I'm not the only one who thinks that way. But the space agencies are looking along these lines, and I think that much of the stuff that we're doing in planetary exploration is actually driven by the idea of finding life in a place other than the Earth, and you can convince yourself that the exploration of Mars, I mean, the big program that NASA and also ESA and JAXA are having is mostly driven by that idea. Can you find habitable conditions and life, at a planet other than the Earth? And Mars is your favorite target because it's close by. You can relatively easily get there. And in comparison to Venus, for instance, it is a planet that is at least, or has been to some extent, habitable in the past. Now, it is of some philosophical relevance because you can argue that finding life would complete the Copernican and Darwinian revolutions. and put our human existence into perspective. So we're not the only ones, we're not the center of the universe, rather we're just one of many manifestations perhaps of the highest organization form of matter in the universe, perhaps. What is important, of course, is that finding or the search for extraterrestrial life, rests on some research of understanding, and predicting, very confined. So when you talk to people who are looking, like for instance in Antarctica or in other desert parts of the world, for finding life there, they speak about finding like the needle in the haystack, and it helps if you have an understanding of where to look, if you can do that when you go there, and the same of course applies to Mars. And in the background here you see Giordano Bruno, who's got burned in Rome, 500 or so years ago, because he was one of the first to promote the idea of that we're not alone on this planet, but there may be other civilizations in the universe. And here is a picture of the ExoMars Rover Pasteur that is set out to find extant life on Mars. Now this is a picture actually from where I live in Berlin. Berlin is a pretty green city actually. You're looking across the River Spree to the Treptower Park, and you see some of the things that set the Earth apart: water, fauna, and flora. And if you look at Mars, today, this is a picture of our high-resolution stereo camera that we're operating. My institute is operating on Mars Express, and you see that today Mars is a cold desert. And how to understand, why this planet here is looking this way and Mars is looking that way, and how this came about, and what the chances of still finding some traces of life here in this desert is, of course, one of the motivations that drives us to this research. I want to speak about habitable zones and the ideas of habitable zones. I don't know if anybody else introduces the concept in this series of lectures, but I'll start in doing so. And I'll pick up at where Cyril left us this morning, talking about metallicity in stars. And actually people are using the concept of, on the one hand, looking at the metallicity of stars, and on the other hand, looking at supernovae and balance the two to see what is a habitable zone in the galaxy. So there is this definition of a galactic habitable zone, introduced first, I believe, by Gonzalez and others. And there's a recent paper just came out by Forgan et al., who through model calculations came up with this evolution of habitability in our Milky Way. It's hard to read actually on this screen, but they plot the number of planets that remain in Clement, that means habitable conditions, as a function of the place in the galaxy. And you see that actually the most clement or favorable conditions are relative close to the center of the galaxy, although there should be the black hole. That's of course not a good place to be. But anyway, I mean, there apparently you're shielded by the sheer number of stars, from the effects of nearby supernovae. And you have enough metallicity there, planets there with high metallicity, or stars with high metallicity that allow the formation of planets in order to actually produce terrestrial planets. So that is an interesting finding. But there are other, in the arms of galaxies, there are other cores of habitable conditions. Now, I'm not an astrophysicist, so I can't really judge that from a critical point of view, but as a planetary scientist, I find it interesting that we're used to looking at habitable zones in planetary systems. Now we can look at habitable zones on a galactic scale. Now, moving on to the habitable zone in a planetary system, there is this thing called the circumstellar habitable zone, CHZ, or SHZ, the stellar habitable zone. People use this definition of that interchangeably, I think. And it is defined as the distance from the host star where temperature and pressure conditions allow for liquid water to exist, and I should have said here, on the surface. Okay, so you're looking at planets, the surface temperature of which in their atmospheres allows for the existence of water. And here we have the water phase diagram, and you can actually see that here is the Earth, and the Earth is at a pressure and a temperature range that allows for the existence of liquid water at the present time, while Mars is very close to that triple point here, and actually there is only thermodynamically at present time you can only be in the vapor or gas phase or in the solid phase. Here's vapor, here's solid. You know, these concepts, you know, differ a little bit from whatever paper you're reading. You know, some are very sophisticated and moving the Earth, you know, in a distant range, you know, about its present center to map the boundaries, the inner and outer boundary of the habitable zone. Others have more simple concepts of the atmosphere, but in any case, you're including you know, the greenhouse effects in that, and then calculate the surface temperature and check that with a phase diagram of water. Now there is a little bit of weirdness in there, if I may say so, because you know this definition actually allows you to go up to the critical point here, and if you moved Venus a little bit and put it right here, then of course there would be liquid water on the surface. However, these temperatures, you know, are much larger than any temperatures that, according to my understanding, and I'm not a biologist, you know, any living things, proteins and so forth, would actually support. So, you know, you could probably argue that the inner boundaries of the habitable zone should be defined maybe a little more stringently. Anyways, I mean, this the habitable zone is then a function of the insolation by the star, and that insolation rate or luminosity scales with the mass of the star. And there are certain, we heard this morning in a very nice presentation, you know, how the luminosity varies with the mass of the star and the type of the star. We're here at a typical G star, I understand, and here is our solar system. And here are the three planets that, in a very generous interpretation of habitable zone, would lie at the border of it, Venus and Mars, and the Earth, of course, right in the middle. Now, this has been put together by Heike Rauer from my institute and others. And what they did, they plotted, you know, some of the planets from other planetary systems in there, and of which we know well, no, not all of them. They're from the transit method and the radial velocity method. So we do not know from all of them what their radii and their masses are, but from them, some of them, we know the mass, and from some of them we know the radius, and actually we would like to have both. But anyways, so there are some, you know, some of them have been detected, and I think they're probably, this is not the newest slide, there are probably more in the meantime that cover habitable zones, but most of the planets, I have a slide later that shows that are found there are actually giant planets, and what we're looking at, assuming that giant planets are not necessarily what we're interested in talking about habitability, we're looking at terrestrial planets, and these are still relatively scarce. Most of the planets, and we heard that this morning, that, you know, the smaller stars are more popular or more populous in the universe, and therefore, you know, much of the discussion goes about planets around M stars. They're typically close in. That means they're easily detectable, relatively speaking, in comparison to planets around G-stars that are further out. So much of the discussion is then about the habitable zone around M-stars. However, there is as I understand it, quite a different radiation environment around an M-star in comparison to a G-star, so that even if you had a significant number of planets in the habitable zone of an M-star, you couldn't be sure that they wouldn't be bathed in radiation and life would actually be possible. When one talks about this concept of habitability, then one should be aware that at least in our solar system, that there could be habitable niches, in other places. And one of these places is the subcrustal, or no, not the subcrustal, but the subsurface depths of Mars, for instance. We know that life can exist, from the pressure on the Earth up to a depth of about 3 kilometers. And on Mars, that scales to 10 kilometers. So if we then are sure that we won't have liquid water on the surface of Mars, but how about a depth of 10 kilometers? And it's easily possible to envisage that here you may have liquid water, and therefore there may be niches, habitable niches, in the subsurface areas of Mars at depths of a few kilometers. Unfortunately, these depths would not be accessible for us, at the present time. And therefore are out of our reach. But that is, of course, a possibility. And other possibilities of possible habitats outside the habitable zone of our solar system are, the well-known cases of Europa and Enceladus, where you are definitely out of the habitable zone, but still, you have water, oceans underneath ice layers. You may have the right temperatures, nutritions, and so forth, and you may actually have habitable conditions. This has led some people to say that, well, the habitable zone is everywhere. Now, that is perhaps a little bit of a too extreme point of view, but one should be aware that this story does not cover the whole picture. Now, there are other requirements in habitability rather than water on the surface, although I would agree with many who say that certainly, from our understanding of biology, water is the most important, next to carbon, perhaps substance for life as we know it, and therefore it's an easy indicator of habitable conditions. But for life to evolve, beyond the primitivist forms, you may ask for more, and that would, of course, include, for instance, the stability, of climate. Obliquity variations of the rotation axis could be a factor here, which Mars has suffered from excursions of that. We have the moon to stabilize our rotation axis and prevent us from large excursions of the rotation axis. Carbonate silicate cycle, so that is basically plate tectonics operating, and other geochemical cycles that would stabilize against excursions of the climate. A continuous supply of nutrients, surface rock renewal, could be an important element here, so that whenever stuff is eaten up, basically from the base of the food chain, that you renew it and provide new nutritions. The magnetic field is often cited, although I tend to side with those who say that this is often perhaps over stressed, because there is harmful radiation that the magnetic field doesn't help you against, and it's basically the atmosphere that protects us. However, the magnetic field, of course, protects the atmosphere and, more indirectly than, protects the biosphere on the surface. Geological diversity is an important element, at least as far as we understand, and we don't have a deep understanding of the origin of life, but geological diversity is certainly a driver that allowed formation of life on this planet, but it's also probably at the heart of keeping life alive, and I will speak about continents a little later versus the end of my talk. And then, of course, there is impact and other cosmic hazards need to be low. Now, that is something that there's little to be done about other than saying that we have a disaster plan. And actually, I mean, there are people looking at disaster plans, and there are also, like other space agencies, are looking into these issues of how to, perhaps, I mean, if an asteroid comes by that is, to be detected early on, how we could divert, its path if it is on the way of hitting the planet. And actually, the United Nations have a program that is looking at this issue. And, it's something that concerns people, and with certainly some right to do so. Now, in many treatments of habitability and astrobiology, you see that the claim that plate tectonics, could be important. And certainly, considering what I said in the previous slide, in many of these things you had plate tectonics, actually tacitly involved, like in the carbonate-silicate cycle, the magnetic field generation, the continuous supply of nutrients. There's all this, in a way, at least on this planet, related to plate tectonics. And what it does, and I will speak about plate tectonics more in the remainder of my talk, but what it does is it recycles near-surface rocks and volatiles to the planet's interior through subducting, crust into the interior and continuously forming new crust. And that helps to cool the interior and drive the magnetic field generation, the dynamo. We will speak about that. It creates geological diversity. Continents are, in our understanding of the geology, a manifestation or a result of plate tectonics operating on this planet. Although, there is, still, to develop a deep understanding of how plate tectonics started and how continents came about. But our present model of the growth of continents, at least, is tied to the plate tectonics concept. We replenish surface rock through plate tectonics, we stabilize the atmosphere in the carbon-silicate cycle, and we help to generate the magnetic field. Now, before we go into the detail, let me speak about another habitable zone definition that I just learned recently about. I know, actually, I couldn't find out whether these authors have created or coined this term now, or whether it may be in the other wider astrobiology community it is already introduced, but they speak about a biogenesis habitable zone. So a zone wherein conditions are just right to have life emerge. And it is not a zone in a strict sense of a distance, but rather, as I understand it, is a range of physico-chemical parameter values that allow for the formation of life. And, as far as I understand, it is not as well defined as the CH set, for instance, or the SH set. And that may have to do with the problem that we're not really having an accepted theory of the origin of life. Anyways, this is a representation. It's from their paper of some of the ideas that they have, and I found this quite interesting. So in a plane that is spanned by parameter values, whatever they are, you define, and this here is time, you define a subset of parameter values that defines you a abiogenesis habitable zone. Though these at 4 billion years ago, these are the conditions that led to the formation of life on this planet. Now, they don't care whether you say, well, it was only 3.5 billion years ago or 3 billion years ago. You know, sometime in the past, I mean, you formed life on this planet. Now, they're saying that usually conditions move away from this set of parameter values. And I don't know if that is true. I think that can, of course, be debated. But it may be so. And that would mean that the genesis of life could only happen at some, range of time, so to speak, in the life of a planet, and then later it would no longer be possible. But then, of course, what they introduce is the concept of maintaining life. And here in this, you see that there is a wider defined range of values of the planetary environment, but then there is a subset of habitable conditions that may not coincide. It does in this plot, but it may not fully coincide with what the planet does. And another representation of that is on the right-hand side here. Though this is the habitable conditions, and assume that they, in the sense of the circumstellar habitable zone, assume that they are constant in time, that they would not evolve. And here are the planetary conditions, and then you have the abiogenesis habitable zone right here. So they coincide, all three coincide for some time, but then the actual planetary conditions move away from both the abiogenesis habitable zone and the circumstellar habitable zone conditions, and life would then disappear on this planet. So this may have happened on Mars, that actually you had, for some time, the condition to form life and to have a little bit of time to evolve it, but then Mars went dry and cold and just moved away from the nice region here. Now, they're arguing, and I actually have a lot of sympathy for that, that this form here, this what do you call that? A hose or something, could be deformed, by the action of life itself, to allow for life to exist further, and that the extension of it could actually move in time. So there may be conditions that would be more habitable than at other times, and at some point in time it may go away, and the planet may evolve away from the habitable conditions, and then life would die on the planet. And they're arguing, and therefore they call it the Gaian regulations, that life itself, may be active in stabilizing habitable conditions. And of course, that life plays a role in the carbonate silicate cycle by fixing carbon in carbonate rock. And that, by stabilizing the temperature on the planet, may be one way of how life, acts to stabilize the habitable conditions on this planet. You can then, of course, discuss that and ask yourself, why does that not happen on every planet? So and I think they're quite reasonably arguing that it is a matter of the biomass. If the biomass remains small, life cannot act to modify the conditions on the planet. But if life, evolves quickly enough, then life could pick up and maintain the habitable conditions there. So I think this is quite an interesting concept, and in a way it coincides with some of the stuff that I will show you versus the end of my talk. Now here is a little bit of a more detailed explanation of what they're talking about. They're looking at the temperature on the planet and the time since the planet formation. And here are certain models, that show the evolution of temperature, starting somewhere around here, and then excursions in the early evolution of the atmosphere. And then you may run into a runaway greenhouse and leave the habitable conditions in that way, or you may fall into a runaway snowball effect and leave by that way, and only if you have a feedback mechanism that stabilizes temperature can you then extend your time within these bounds that define your habitable temperature conditions. And here is today, and people were talking about what's in the future. So in the future, according to this model, probably because the sun grows and becomes a red giant, temperature becomes too hot, and then we're leaving this, and life will then die on this planet. Now they go on to speculate about the problem that Fermi had put out. Why are we not finding many civilizations in our neighborhood? And of course there is a possibility that they didn't form, but it is also possible that they formed but then got extinct. And but I don't want to enter into that discussion in my talk, actually. Anyway, so this is an interesting concept, and I think the stabilizing effect at least has a lot of sympathy with me, and I believe that there is something there to be further explored, even beyond just the carbon silicate cycle itself. Now, just to summarize that a little bit, so we may have habitable planets in the habitable zone, like for instance Earth with all its workings, interior workings, magnetic field generation, plate tectonics and so forth, and it's our standard model of a habitable planet. We are oriented in our thinking along the Earth, which is perhaps a little dangerous because planets could function otherwise, but of course we're from our own experience, we're sort of biased towards this picture of it. And here is a habitable, or what people think is a habitable planet, at least from the sheer definitions of having water and other things of Europa, where you have moon of Jupiter, where you have an ocean covered by ice, protecting it against the ocean against the cold temperature in the Jovian system and the harmful radiation from Jupiter and so forth and so forth. And also, I mean, the nice thing about Europa that sets it apart from the neighboring moon Ganymede and Callisto, that also are believed to have oceans, is that here the ocean is in direct contact with we believe at least so, in direct contact with the rocky part of the planet, and therefore you have all the chemistry that can be used to derive nutritions and feed your possible biosphere in there. And people have calculated models then and looked at whether the nutritions would be able to support the small biosphere, and yes, it seems to be that way. Also, the question of energy, of course, is important because, and I actually didn't mention that yet, but energy, of course, is important. On the Earth, we have solar light. We can use the photons from the sun. We, of course, have very little, lighting here in Europa, but we have tidal energy, and that may be sufficient, to at least power a small biosphere in there. In order to discuss these things, and therefore I think the title that Muriel chose for my talk is very much applicable. In order to discuss these things, we need to look at two issues. We need to look at the formation of planets, so how do we get wet, rocky planets in the habitable zone, and that are not bothered by inward migrating giant planets that would kick them out or force them to become their moons, in which case then the evolution of life might be at least much more complicated than if there are planets in their own rights. And then we need to look at the workings of planets as they co-evolve with life, and look at something like this Gaian bottleneck that Chopra and Lineweaver were addressing. This is the slide that I was already alluding to a little earlier. This is a little complicated manifestation of basically what the habitable zone in terms of the stellar temperature, which is another proxy for stellar mass, and stellar flux, which is a proxy for distance from the planet. You know, if this is your habitable zone, you know, so to speak, then runaway greenhouse or extending to that. I mean, the point that I want to make here is from what we know about exoplanets, you know, there are a high number of giant exoplanets, you know, in these regions, and you know, we're not too pleased by them because you know, they are migrating inward and disturbing whatever nice little, you know, terrestrial planets you might have in there. So there is probably something like a habitable, not only a habitable planet, but also a habitable planetary system, you know, where you have the terrestrial planets at the right place. Yeah, I wanted to give you a little bit of a few textbooks that I, you know, at least find interesting in the context of planetary sciences and planetary geophysics and astrobiology. This is only a subset of what's available, but you know, if you want to take a recommendation, then maybe Imke de Pater's and Jack Lissauer's book I find very interesting. Also, Jonathan Lunin's Evolution of a Habitable World. It's more like geophysics is not so much planetary, but still, I mean, it discusses astrobiology. Bill Hartman's Moons and Planets is a classic in this field. Thank you very much, Muriel, for you know, giving me this morning this book. So I put it into the list. I have to say that I haven't read it, but I scanned through it, and very nice pictures, and it looks very promising, so I put it in there. There are, of course, a number of textbooks in geophysics, geochemistry, and geology that I don't want to mention. There's an interesting collection of articles in a book, Planets and Life, you know, by Woodruff et al., that I at least consult. And then this is a commercial. We have the Encyclopedia of the Solar System that came out in 2014, the third edition. It is actually not so much an encyclopedia in that you can pick up, you know, various things and look at their definitions, but rather 1,000 pages of articles on anything related to planetary, solar system, astrobiology, and so forth. And I just wanted to put your attention to it because it was so much work to put it together. And then, of course, there is the Encyclopedia of Astrobiology that Muriel is editing together with others, and I have the privilege of being one of the editors of it as well. Now, while the Encyclopedia of the Solar System is, you know, suitable for students and also, you know, laymen's, you know, because I mean, it doesn't go too much into detail. It's very convenient. I at least use it, you know, to read if I want an introduction into a field that I'm not too familiar with. I mean, go to this 5 to 10 pages, and you have at least a modern understanding of what's going on and, you know, what the basic things are. The Treatise on Geophysics, Volume 10, is also about planets, and this, of course, goes much more into detail and depth. And so if you're, for instance, interested in the thermal evolution of planets, you might start with that here, get a feeling whether that is something you want to look further into, and then you can consult this thing here, and there's another article on the thermal evolution of planets, but that is much more detailed and goes much more technical and so forth. Anyway, so I hope that maybe this is useful. So formation. Now, our understanding of solar system formation, as I understand it, I have to say that I'm not really active in this field. I'm looking at it with a great interest, and I'm trying to, you know, teach some of the basics whenever I get to teaching a little bit. You know, it's basically still, you know, what Immanuel Kant and Pierre de Laplace proposed, you know, in the 18th century, and I understand they developed that independently of each other. And they're looking, you know, they propose that the planets were formed from a nebula under attracting and repulsive forces. Now, attracting is gravitational, and repulsive is, I mean, you know, the collisions of planets. And that is still, you know, the basic idea of what we're having as our understanding of the formation of the solar system and planetary systems. But the details of this is a subject of ongoing, very intense and very interesting research. And there have been a significant, evolutions of the concept over the past years. And I think that in the last 10 years or so, or no, it's a little longer than that. I think that started in the 80s with the work of Wetherill and others. I mean, this has really picked up and is a very active field. Now, this is science, so you need constraining observations. Of course, there are samples, meteorites, in the planetary dust particles, cometary nuclei are of interest, asteroids, planets, and so forth. So, whatever is to be found in relevant observations on these bodies, is of course something that, the models of planetary formation, need to fit. So for instance, something like the late heavy bombardment, needs to be explained by that, or, isotope variations and so forth and so forth. Now there are collections of meteorites that are of course available, and here in the background you see people collecting meteorites in Antarctica. So they're still, on the search and on the hunt for these rocks. Missions to primitive bodies, like for instance Deep Impact, our Rosetta mission that will end this year, has implications for planetary formation models. Hayabusa, the mission, and Hayabusa 2, the follow-on mission that has been launched last year, will provide data that constrain these models. Dawn, OSIRIS-REx that is on its way, the NASA mission that's on its way to a asteroid, and Dawn, of course, was visiting Ceres and Vesta, as you probably know. Comparative astronomical observations, system of exoplanets, young stars and their environments and so forth, lab studies, mass spectrometry and so forth, and then of course modeling. The modeling, I'm a modeler, by training, so that is something that I am mostly interested in, and therefore, my talk will be more on the principles of these models than on these other things that I still find very important. So I started, basically with Zavronos gas dynamics models, where you had the evolution of a cloud of gas to a disk, and then condensation in the disk, and he got the planets from discussing the gas dust nebula to then studies that looked at an ensemble of planetesimals, and like 100 or so, which is what Wetherill started with, and then looked at the orbital dynamics and interactions of these particles and how they agglomerated and eat each other, got destroyed, and so forth. And one of the popular things that are around and is discussed is, for instance, the Nice model, or one should actually say it's more like a family of models, because when you look it up, the Nice model actually is a model to explain the Kuiper belt. It's not a model that explains the solar system, but variants of the Nice model, have been broadened and discussed much more than the original papers that popularized that name. And that France, Nice is the city in France, that where this work was first done, and of course France and Alessandro Morbidelli, of course, and others, played a major role in that. A variant of it is the Grand TAC model that I will briefly come to. And then there is a relatively recent development is what they call the pebble accretion model. And the pebble accretion model bridges a gap that the other models have, and I will speak a little bit to that. Now, important elements of the theory of the formation of planets is you start out with the nebula, and the nebula collapse to a rotating gas disk. Then condensation and growth of solids, thermodynamics, sticking of particles is an important area of research. The sticking of particles is a very You know, it's problematic, and people like Jürgen Blum in Braunschweig in Germany and others around the world, you know, spent their careers in trying to understand, you know, how through electromagnetic and van der Waals forces small particles would stick together. Then, you know, the Nice model and their varieties are basically orbital dynamics, you know, of multi-particle ensembles. And here you have, of course, Newton's laws and Kepler's laws. I mean, it's basically Hamilton mechanics, what they do. Viscous drag between the gas and the solids is important, and this is, I think, what the Pebble model has highlighted. Gravitational interactions between the bodies and the growth by collision and sticking and gravity and destructions through collisions is another important element of all of that. So we start this by having a gas and dust nebula, probably only gas in the beginning, and then the condensation of matter in that hot nebula, fed by stellar explosions. Isotopic inhomogeneities were partly removed by mixing. Then the nebula collapsed to form a rotating disk and the action of probably a near-stellar explosion. Details are a matter of research. The mass concentrated in the center. Today, you know, in the solar system, we have 99.86% of the mass in the sun. But, you know, during the evolution, the angular momentum of the remainder of the nebula was transferred from the sun to the remainder of the nebula, such that 99.5 of the angular momentum of the system is in this other part, not in the star, so in the solar system, through gas track and magnetism. And here is a picture of the Orion Nebula with you know, forming stars in there, and yeah, okay. Now here is our again from the Orion Nebula, and all these have an extension of 400 AU. And you see, you know, young stars with their disks surrounding them, and they're different in their you know, temperature and mass, but they're all, you know, about the same age. And this has been taken with the Hubble telescope, and there are you know, and oxygen is bluish, so you have a lot of oxygen in this. And hydrogen is greenish, and nitrogen is red. So wherever you know, you have a reddish tint to it, then you know, you would expect that this indicates hydrogen. Now this is from Mark McCaughrean, who's now playing a leading role at ESA, and when he was still at the Max Planck Institute for Astronomy in Germany. For the discussion of the evolution of the nebula and the planets from there, we need to gauge the time. And this is an important element of saying, you know, when is time zero, you know, in these models. And it has been agreed that the time or the age or relative to the present time of the so-called calcium aluminum rich inclusions, which were you know, among the first solids that formed in the nebula, that their age should set time zero, which is this number in here. And of course that matters for processes that you know, are or have been going on in the Earth system. For instance, the decay of heat-producing elements like aluminum-26 or iron-60. And you know, their half-lives is very short. So you know, it matters, as you will see later, you know, how you are you know, positioning yourself, you know, relative to that time zero when you are actually forming these planetesimals. And you can see here in comparison, I mean, this is a plot of those elements that are powering or heating the planets today, and you see that their decay on that time scale doesn't even really show up, you know. I mean, so this is the short-lived isotopes in comparing to the long-lived isotopes. So anyways, I mean, the point that I want to make at this point here is that this is our time zero relative to our present time. This is a rendition or some pictures of how these first, solids may have looked like, from meteorites, I guess they have been collected. This is an idea of what was going on in the nebula at the time. So you see that the gas in here, you see that there are smaller bodies and larger bodies, that larger bodies are colliding, smaller bodies are colliding as well, but you form smaller bodies through these collisions, but you also stick some of the stuff to you, and through the process called oligarchic growth, you're having the bigger ones eating the smaller ones, and then form from the planets from that. And here is sort of a little cartoon that shows, two bigger ones going through here and smaller ones on different orbits, and some of them are attracted towards them and are then eaten by the bigger particles. Also, if you have bigger particles passing by through the action of gravity, you slow them up, and then they may, with the right conditions, may collide, and if the collision is just right, they may stick to each other. If the collision is too powerful, they would destroy each other and then, form some of the small stuff here. But in the end, when you do these calculations, you usually get some runaway growth, of the large particles at the expense of the small particles. And you end up with something like that here. And this is a representation of a numerical model that goes back to George Wetherill in the 80s. So there is a accretionary mean lifetime, which is the reciprocal of the time constant for an exponentially decreasing oligarchic growth rate. So if that growth rate decreases in time, then you form, depending on the tau parameter here, you form, like for instance, a planet like the Earth within about 40 million years or so. And you can gauge these, the various taus that you do not get, easily from your model calculations. You can gauge that, from, for instance, hafnium tungsten isotopic determinations of the time or formation of the planet, including core formation usually, and you can compare that, and then you end up with a preferred model that would go something like that, and you would then conclude that, well, yes, we formed the Earth in that time span. How are we doing in time? Okay. Now, this kind of models, they have a kind of unpredictability in it. So they do not necessarily, end up with the right planet at the right place with the right composition. And here is a representation of that. So assume that you start with a nebula that is ordered according to red, yellow, green, and blue components. And if you don't like it, in that way, you think that this is very refractory, like iron, something like that, and you assume that there's a temperature gradient in the nebula, so you have the stuff with the high condensation temperatures right at the center, and then as you go out, you have the increase of the volatility, so that you have water, ice, and so forth out there. But for the purpose of this, we can just call it red, yellow, green, and blue. And then you have these models run, and you see that these are various outcomes of a model calculation like that. So you may end up with 3 planets, and a small one out here, so 2 big ones, 1 small ones. and it would be composed of this, and this sounds a little logical because the reddish stuff is making up at least a third, and it's more, this one is redder than that one, and this is formed in the interior and so forth. And here you have 3 planets, and here you have 4 planets, and you have this bluish one out there, and here is another that actually looks a little bit like the solar system, with the 2 small ones and the big ones in between. But the point to make here is that actually you cannot easily say, and this I think was one of the recognitions that Wetherill actually made, because before Wetherill we had understood, well, look at Mercury. I mean, Mercury has a lot of iron. It has a big core, and that's okay because it's been formed close to the sun, in the hot condition in regions of the solar system. And then we go outward and we see the chemical gradient. But Wetherill showed actually that you can actually have Mercury form right here, and then late in the evolution be through some gravitational interaction with the neighboring planets, be brought to that place. And it is not clear in these calculations that you necessarily end up where you started when you formed. And one famous result of that, for instance, that was done by the Nice model, is in the Nice model, if you look at the classical Nice model, Uranus and Neptune changed positions during the evolution of the Nice model. So that Neptune was closer in and Uranus was further out, and then they changed position. So that is entirely possible in these models, and therefore there is some you get manifolds of various solutions from them. But still, I mean, if you look at these large families of models, there are trends of things to be recognized, and this is actually what then people look at, and when they're concerned about certain features of their models, this is actually what they're concerned about. And one of them is, and I will come back to that later, is actually the small mass of Mars, and that is something that according to the expert in the field should actually not be the case. If you don't have any extra effects, and much of the research that is going on in recent years, including the Grand TAC model, also this Pebble model, and it was motivated by finding an explanation why Mars is so small. And you see in these models here, it would not be so small. Here's another one, but this doesn't fit because these guys are too big. They're usually not so much concerned about Mercury. The reason for that, and this is my speculation, probably is that Mercury is formed so close in to the sun, though that conditions are special there anyways. So that doesn't really concern people too much, but Mars apparently does. Okay, now in the evolution of this theory, there is an interesting transition, and this transition is shown here from a phase where the bodies are so small that gravitational binding actually doesn't really matter because their own gravity is so small that they almost don't attract each other. And in this regime, you have to bind these through van der Waals forces or electromagnetic forces. This is what they call the sticking regime. Here and this is that below a meter or so. And you see that the sticking efficiency decreases, with increasing size because they're becoming too heavy, for sticking, at one point. And at the same time, the gravitational binding, picks up here and increases, with size and mass further on. Now, it's been a problem, for many years, how to get through this gap. How do you actually, in your formation of a planet, get the planetesimal to cross this gap here, and not, stick with, if you start at small sizes, just be stuck with that here. And this is actually what's been, is that my next? Yeah, okay. This has actually been only recently, well, actually recently, it goes back to work that was pioneered in 2007, but that's almost 8 or 9 years ago now. But it's been, explained by what is called the pebble accretion model. And the pebble accretion model, if you think about it, is actually relatively simple. But if you look at the papers, it's not the simple thing, the heart of it is not actually always so easily visible, in the papers themselves. But what's at the heart of that is actually the viscous drag on pebbles and planetary embryos combined with the gravity. So the pebble model would only work if you have pebbles, that is rocks, pebbles, up to the size of meters or so, yeah? And they have to be moving in a gas, in a viscous gas. What happens if you're moving through a viscous medium, you are leaving a wake behind yourself, And in the wake behind yourself, anything that gets into the wake, does not experience the same viscous drag as yourself. Okay, this is what cyclists use, the Tour de France. When they call that the wind shadow cycling or whatever. So one guy cycles in front and the others are lining up behind him. And just the reason for that is they're riding in the wind shadow of this guy. Okay, I actually crossed about this effect a long time ago when I was looking at bubbles in magma, so I was interested in getting magma bodies to the surface, and I read a paper by a famous hydrodynamicist who had expanded the Stokes model of flow around a sphere to include ensembles of spheres, and what they showed is that if you have a bigger one moving in front, the rest just settles behind this guy, and travels in its wake, just like the cyclists do. This also happens with these pebbles. And therefore, if you look at that, then their radius of attraction, becomes much bigger than their actually physical radius. So they are collecting the stuff, in their neighborhood. And putting it, behind them, and then they can catch up with it and merge with it. This is also what you see in these bubbles. That the bubble, that follows the big guy, just moves towards it, and finally, is merging with the big one. You can see that also, that effect when you travel on a railway, and you look at the water on the on the window, and you see little things that, and then there comes another one that moves in the wake, and it picks up speed and gets to the big guy in front of it, and this is actually what's behind that, what they calculated here is, and I have to read these numbers here myself, is that you can increase the radius of action, by orders of magnitude, relative to your own physical radius. And by that, you can sort of form agglomerations of small pebbles that would not gravitationally stick to each other, but move as clouds of pebbles, so to speak, and over time sort of coalesce into bigger ensembles and into planetesimals. And that is an effect that actually crosses this gap, because as an ensemble, then they can get across the 1 meter gap that they couldn't do individually. The effect is that that growth is very rapid. So we can actually go to 10 Earth radii. A planetesimal can grow to 10 Earth radii within 1,000 years or so. Now that was cool from a perspective, because there was another problem in the accretion theory. That was the formation of Jupiter. Apparently, Jupiter had to be formed very quickly. And the current theory of the formation of Jupiter is that you have a terrestrial planet in the gas, and if it becomes big enough, like 10 Earth radii or so, then the gas collapses on it and forms a Jupiter planet. And that had to be done before the gas went away, and the gas went away like 10 million years or so after the formation of the nebula, after CAI. And you couldn't actually, and we've seen this in the previous, according to the weathering model, you cannot form these cores so quickly. So therefore, you needed a more effective model in the outer solar system. And the Pebble model just came right. Now, there's still a problem with that, and that has recently been solved, and some of that is can help to overcome the meter barrier and explain the rapid formation of giant planets by allowing planetesimals to rapidly accrete pebbles. This is the 2015 paper. There was one problem. If you make it too quickly, you're not forming like 4 giant planets, you form 20 of them. And that wouldn't fit. So in the meantime, they have a little bit of a problem of steering this such that the accretion of the pebbles is rapid, but not too rapidly. And if it's just right, then you get the right size, number of Jovian planets in that. And there is also a most recent calculation that explains the small size of Mars to that. And this has to do with this figure here on that side. Though there is the effective radius of a pebble is an exponential function of this parameter here. And this parameter has to do with is the stopping time. That is the time that a pebble is a measure of the viscous drag on the pebble in comparison with its encounter time, so the time that it spends in the neighborhood of a passing by a planetesimal. If that becomes big, then of course your effective radius becomes small. I don't want to go in too much detail, but just to say that this is a function of the distance from the central star. So as you go out from the Earth towards Mars, you decrease the effective radius, and therefore you're growing a smaller planet. Now there is also a difference between the outer solar system, where the velocities of the planets are smaller than in the inner solar system, to which that applies, so that you don't have to be concerned about forming 10 Earth mass size planet in the inner solar system. That would only happen in the outer solar system, where this range applies. Okay, so if you're interested in the detail, check these papers out, and there you'll see it. Okay, the evolution of a planetesimal, then if you're looking at one planetesimal itself, can be described by something like that. So you form the planetesimal, and then it can have its own life. That's something that we haven't really looked at it so far in this lecture. So it may heat up, and may differentiate, and finally get disrupted. So what we need to introduce into our thinking, not only look at the formation of bigger ones, but at the evolution of those planetesimals itself. And so you go from accretion of dust particles, to compaction, to partial melting with aluminum-26. I was alluding to that, latent heat effects and so forth, convection, and finally you could destruct it or grow to a planet, depending on what the fate of you as a planetesimal is. some of the planetesimals that are still around is Vesta, Lutetia, Itokawa. This is the Hayabusa asteroid. We still see them. But here is a cartoon that Vladimir Neumann, is a student of mine, and Doris Proyas has come up in a series of papers together with us in recent years. And to illustrate that, you look at this thing here. What you plot here is the accretion duration, so the time it takes for your planetesimal to form, versus the onset time relative to time 0, which is the CAI time mark. If you form that planetesimal, early, so close to the to 0, defined by the CAIs, and you form it slowly, fast, excuse me, fast, you are in this red regime. And this means that aluminum-26 can heat the planetesimal, you can melt it, you can differentiate it, and you form a miniaturized terrestrial planet with that. You have a regolith on top that may be sintered, you have a partially molten silicate mantle, and you have an iron-sulfur core. Now, as you start later in the accretion, you're getting into incomplete differentiation, or no differentiation at all. So if you start late and take a long time to form, you're ending with a planetesimal that is undifferentiated but has some porous regolith on top of it. And actually, we find all that in the asteroid belt. There's a whole variety of things in the asteroid belt that is matched by these scenarios. You can put that in more detail and have the convection and so forth, but in the interest of time, maybe I skip that. But why is that interesting? Now, first of all, to explain the asteroids, the observations in the asteroid belt and the meteorite record. Okay. Then, of course, the question how small a body can actually be differentiated. And that here is, to me, the most important thing. Can you imagine that the terrestrial planets formed from differentiated planetesimals? Okay. Because in the old scenarios of formation of a terrestrial planet, you form them from undifferentiated planetesimals, and later you differentiate the complete planet by forming a core. Now, in the more modern view of it, you form these planets actually from differentiated planetesimals, so they have little cores to begin with. So you are, so the core formation process for a planet can be totally different, whether you start with that or that. And it's important to line out the conditions for these. And then another thing is the question of how small a planetary body can actually have a self-sustained magnetic field, because there have been reports of findings of magnetized material, meteorites from planetesimals, and it has been proposed that actually a planetesimal could actually support its own magnetic field. And in a scenario like this one here, it can, because it has a hot core, iron core, and it could have a dynamo in there. Okay, and this is why this is interesting. Now, there is a mission proposal now on its in the consideration for the next discovery, NASA discovery mission. It's called Psyche. The PI is Linda Elkins-Tanton. And it proposes to go to a remnant of a collision with a differentiated planetesimal. So it's an iron asteroid, basically. And it would fly by in about 2020. And this is what people think a crater might look like on it. So it's like a melt, an iron melt that is extruded and forms, this crater thing here. So it might be very interesting. Before I end with the formation part, let's look a little bit at migration, because that is important in the discussion of habitable planetary systems. Though there are basically two types of migration. And migration means that You decelerate a planetesimal and a protoplanet through cavitation interactions with gravity waves in the vicinity of it. So, when a planetesimal moves through the gas, I mean, it can be decelerated by viscous drag. Yes, we've had that already. But it can also clear, a surroundings and then move the stuff to the side. And then you have, density waves, in neighboring you. And any asymmetry in that can actually cause, the transfer of angular momentum, and you can move inward in the type 1 migration or outward in the type 2 migration. So basically, it's the interaction of your forming planet, with the rest of it, and that can cause, the inward migration of giant planets, but it can also cause an outward migration. But what we're seeing today, in these exoplanetary systems, with the large number of giant planets that are very close to the stars, is generally explained with type 1 migration having acted, so having brought them close to their stars. It's said that they cannot actually have formed there, but through this migration they've moved inward and then arrived at the present location. And this is an important effect because it has an effect on the habitability. There can also be direct gravitational interaction between planets and planetesimals in orbital resonances, and these effects are, basically at the heart of the NICE model, the Grand Tech model, this we've already seen. We'll look at the Grand Tech model here. First of all, can I start this movie? Oh, let's explain first that, and then we look at the movie. So the Grand Tech model looks at Jupiter and Saturn. It starts out with Jupiter, Saturn, Uranus, and Neptune, and then it has Jupiter move inward and get into this belt of rocky type material, and Saturn moves behind it and catches up to it, and it moves, this S-type material, it moves out, okay, Grand Tech means a rapid, reversal of the movement. When the two get in resonance, they move outward together, and then scatter the C-type or the volatile-rich stuff in again, and therefore you form an asteroid belt that has these two components. And this is, the basic story of the Grand Tech model. And here you see, what's happening here. So you see Jupiter move in, and then Saturn comes in, and then they move together, they move out and disperse, this material and cause the late heavy bombardment and so forth. And there is a paper by Hansen and others that, said that if you have a compressed cloud, so to speak, of rocky planetesimals, you can form a small Mars. So the Grand Tech model also forms you a small Mars. Not only the Pebble model does that, but the Grand Tech model can do that too. And also it causes, it explains the late heavy bombardment that we'll take a look at later, and the formation of the present structure of the asteroid belt. It would also, and this is the astrobiological relevance, it would also stop Jupiter from moving into the habitable zone of our solar system and having destroyed, what is our habitability today. Okay, so the formation part, in summary, Laplace, sorry for that, you're in France, oh my God. So Laplace is still generally valid. The theory has evolved from a gas disk accretion models to the modern many particle simulations. The NICE model actually is a model of the evolution of the giant planets and dispersal of the Kuiper belt, but there have been variants of that explain much more. One of them is the Grand Tech model, the formation of Mars and volatile delivery to the inner solar system, and keeping Jupiter, out from the inner solar system. I should have added here. Another popular form of it is the pebble accretion model that fills the 1 meter gap by introducing gas-pebble interactions. Formation of the giant planets can be explained by that, and the smallness of the mass of Mars. Now I think I've reached the... Okay, no, I should say that too. The chronology of it. So you form the first parts, and then you form Jupiter, within the first few million years. And before that, the earliest objects, magmatic iron meteorites, as cores of planetary embryos, have been formed. Mars also forms pretty early. This is all based on hafnium, tungsten, and other isotopic systems. Latest time for the completion of Saturn. Earth forms relatively late, and then the latest, relevant to us, of immediate relevance is the formation of the Moon, with the Moon forming impact. And you see that a lot of this stuff occurs in the first few million years, and then it disperses over the first 100 million years or so, generally speaking, to form the planetary system as we observe it, at least in its organization today. And after the Moon forming impact, we get then 500 million years later, or a little more than that, we get a late cataclysm of things. This is the late heavy bombardment that may have been caused by Jupiter and Saturn moving outward. But there are also competing models that have many cataclysms or a longer time scale for the decrease of the formation, although this is a little bit at variance, with this idea that most of the planets formed pretty early on, and they wouldn't, do that over this extended period of time. Okay, now I think it's time for the coffee break, but if you have questions to that. No? Okay.